We have so far discussed the basic features of an operating system which are intended to be used in the context of embedded appliances. Today, we shall look at these features in the context of the complete systems or complete OS packages which are available for deployment on embedded appliances. The basic issue is that of configurability. Given an appliance, no available package will fit all the needs. And we need configurability because the overhead for unused functions be tolerated, because we won't like memory to be used for such purposes. So what is the simplest form? Remove unused functions. And in many cases, you actually have the feature to compile your OS with the applications together. So you can use a conditional compilation to eliminate those modules which are not needed. In a way, what we have that such OSs are organized in modular approach. That means OS consists of a set of modules and you make selection of the modules depending on your requirement. And this advanced compile time evaluation is useful for optimizing the whole system. And object orientation can lead to derivation of subclasses or specializations on the basic functions provided by the core OS. But obviously, testing and verification of derived OS is a potential problem. So the whole idea is what? That you have an OS, a generic version of an OS, and you tailor it for your suitable application depending on the functions that you need, as well as you have to specify, if required, the features of the hardware on which the OS is expected to run. So configurability is a very important characteristic of such an OS package. The other issue is management of disk and network. Not all embedded systems have disk and they are all not connected on the network. But general purpose computing systems invariably have OS and network connectivity. So these two aspects are always made as part of a general purpose operating system. But that is not necessarily true with an embedded system. So what we say that effectively no device that needs to be supported by all versions of the OS except maybe the system timer. Because critically system timer has to be there to manage various aspects of operation of an embedded system. But other devices are actually depends on what kind of application you are looking at. So in fact, that is again another reason for configurability and choice of the appropriate device drivers to be made part of the OS. In fact, if you really have slow disks and networks, that can be handled by tasks. This doesn't form part of the OS kernel or the device drivers that comes bundled with the OS. So if we compare the basic idea wise that if I have an embedded OS and I have a standard OS, so you have an operating system and along with you have got device drivers for a multiple of applications. Here you make choice of the device drivers depending on the devices that you would like to use, and it very likely it would be a real-time kernel, because if it needs to support real-time tasks, the kernel has to be a real-time kernel, which is not a necessity for a standard OS. And in many cases, you will be using a standard OS to compile an OS along with application bundled into a package to be downloaded onto an embedded appliance. Next issue is protection. In the last class itself, we have seen that we can use MMU to provide a variety of protections. Okay. Now, these protections in many cases are required, but also in many cases we may opt to provide a limited amount of protection and not extensive protection as we require for a general purpose system which is expected to support multiple users. Because ES, that is embedded systems, are typically designed for single purpose and untested programs are rarely loaded. So it will not be expected that a program would like to access and memory area of some other process. Software is considered reliable under those conditions. However, protection mechanisms may be needed for safety and security reasons where you want to preserve the option of enhancing the software on the fly. So, related to this protection becomes the privilege mode operations. In fact, in a standard OS, you always have the I/O operations in privileged mode. Okay? That is, that when I am actually doing an I/O, a process, a user task may not have a direct access to an I/O. Okay? But it may be possible for an process which is in an embedded OS to access directly I/O. So, I/O instructions need not be always be executed in a privileged mode. When it is to be done in a privileged mode, we have seen that one mechanism is kernel map. So, you map the pages corresponding to the kernel, corresponding to these device interfaces into the page table of the process itself with the domain memory conditions, domain security conditions enabled. So, in that case, you really do not have a context switch, but there is a switch in the status of the processor for execution. Interrupts are also not restricted to OS. Interrupts can be employed by any process. Since embedded programs can be considered to be tested, since protection is not necessary, and since efficient control over a variety of devices is required, it is possible to let interrupts directly start or stop tasks by storing the task start address in the interrupt table. So, it becomes directly mapped onto the task depending on the application. It can be more efficient than going through the OS services. Obviously, the overhead of the OS service execution is getting eliminated. And so, what happens? Effectively, the software latency for that interrupt service effectively goes down. However, what we say, the composability suffers. If a specific task is connected to some interrupt, it may be difficult to add another task which also needs to be started by an event, in fact by a similar event. So, it can be done if I use OS service to map an interrupt to multiple tasks depending on the requirement. The other point which is a fundamental concern for embedded appliances and systems is real-time capability. So, many embedded systems are real-time systems, and hence the OS used in the systems must be real-time operating system. And what is a real-time operating system? In a way, a real-time operating system is an operating system that supports the construction of real-time systems. And we have already had the definitions of real-time systems, and we know the difference between soft real-time and hard real-time systems. So, what are the key requirements? The basic key requirement is timing behavior of the OS must be predictable. We have talked about the scheduling strategy, but you have to also consider the services that OS provides. Each service has got a overhead. In fact, scheduling services have also got an overhead, and we have considered whole scheduling scheme without considering that overhead. But in actual real world deployment, these overheads play a crucial role. And what we need to have exact timing and predictable timing of the OS services. So, for all services of the OS, we should know the upper bound on the execution time. Okay? So, in that sense, RTOSs must be deterministic. Okay? Then only I can actually talk about correctness of the schedules. Why unlike standard Java? In a standard Java, we had already talked about that garbage collector can come into play at an arbitrary instance of time, holding up a thread which is doing a job or the task that user intends to do. So, that brings in non-determinism, okay? And that is not really desirable. So, such kind of interruptions definitely is not desirable in an real-time OS. Other thing is, there should be short times during which interrupts are disabled. Because interrupts are disabled for a long time, then you cannot actually guarantee meeting of the service constraints of the devices or external sensors, because external sensors, when they are providing an interrupt, it is required that devices are to be serviced within a deadline. If you actually disable an interrupt for a long time period, then interrupt will not be acknowledged and such services cannot be provided. In fact, there has been standards for this kind of real-time operating systems. POSIX is an IEEE standard, and in fact, if I have a OS, my own OS, I would like it to be POSIX compatible so that my applications which are POSIX compliant can run on my OS. And in fact, that is the basic motivation for defining this kind of standards, because actual implementation can vary from system to system, OS to OS, but the basic features, if they can be standardized, then your application can run on a variety of operating systems. The other thing is OSIC. This is Automotive Real-Time OS Standard. This is particularly meant for automotive applications. So there has been standards, and you talk about OSs, or when you are making a choice of the OS, you would like it to be POSIX compliant. And when you develop an application, you will be using the system calls, which should be ideally POSIX compliant, so that they can move from one OS to another OS. That means the portability across OS without much of rework being required. There are a number of such examples which are available today and being used. Windows platform, these are primarily sourced from Microsoft, targeted for handheld devices. Then VxWorks from Wind River system, possibly the most well-known commercial operating system used in embedded appliances. There are a variety of Linux variants. In fact, Linux is now turning out to be the most popular, in fact, on an upward swing for its application in embedded domain. Now, what are the further requirements? The OS must manage the timing and scheduling. What we have found, first of all, is that OS services have a deadline. Then all these OSs should provide the services for timing and scheduling. And OS has to be aware of task deadlines unless scheduling is done offline. That means if you are using a table-driven scheduling, a design time scheduling, then the OS need not bother about that deadlines. But otherwise, it has to bother about deadlines to decide about the priority of the tasks. And OS must provide precise time services with high resolution. In fact, this is a key issue, okay? Because depending on the time resolution that OS can handle, okay, you can have specificity of the deadlines. Try to understand this, because you have a timer and the system may be operating at gigahertz. Timer has got a specific counts, and you have OS have got the internal data structure to maintain the timing information. In fact, you can understand, depending on the size of the data structure, you can actually talk in terms of the time resolution with which you can deal with the deadlines. So, for example, I may have a gigahertz clock, but I have implemented a OS which uses, say, a simple 4-bit to store the timing information internally. In that case, I cannot use time resolution of gigahertz level, okay, for dealing with the deadlines. So, time resolution in terms of your internal management becomes a key issue for managing the schedules, and this is related to your underlying hardware as well. So, what we say, the time plays a central role in real-time applications, and this is also related to your actual time, okay. So, actual time is normally described by real numbers, and if you see, depending on what is the data structure allowed, that means how many bytes being allowed for storing these real numbers would actually determine the timing resolution. And there are two discrete standards that are used in real-time equipment. Now, these are with respect to the physical time, making the references with respect to the physical time. One is International Atomic Time, TAI, and universal time coordinated, that is UTC. Now, this is for a universalization of the physical time when you are using an embedded system which may be networked and working with other systems located at different time zones. Just consider that when you are making a mobile phone call, okay, the time zone, if there is a tariff depending on the time period, the time zone can actually vary from country to country. So, there has to be the timing information associated with the call. Okay, so, that way also the physical times becomes an important parameter. So, how does the synchronization is done with respect to the physical time? In fact, many of the embedded systems and the OSs do have features to synchronize with physical time. One is internal synchronization. In fact, these may or may not really correspond to synchronization to the physical time, but this would definitely correspond to synchronization with respect to a time stamp which is consistent across systems which are dealing with the time stamped data. Fine. So, you can understand that today I am time stamping, maybe right now I am time stamping on my mobile sometime say 10:30, okay, and it reaches a system which is networked, maybe, and it reaches at time on that mobile maybe written 8:30. Now, what is the meaning of these two times? It has reached maybe after say 10 seconds. How do these times be compared if their clocks are not internally synchronized? In fact, this synchronization is a very important problem when you consider a distributed OS and a distributed coordination in a distributed OS. So, similar issues do come in the context of embedded systems as well. So, there can be a synchronization with respect to one master clock, and this is typically used in startup phases, and there can be a distributed synchronization by collecting information from other neighbors and trying to offset the errors with respect to the timing information available from the neighbors. So, it is something like that I look at your watch and as well as your friend's watch and try to find out the best time, and all of us, all three of us can synchronize our watch with respect to the joint agreement of our time. The other issue is that of external synchronization. External synchronization guarantees consistency with actual physical time, in fact across multiple time zones as well. And what is done is nowadays to use GPS for external synchronization. Okay, see, global positioning systems, they do communicate with the timing information also, and it can be even of the order of 100 nanoseconds, the time resolution. So, using that, the physical time synchronization is done. In fact, physical synchronization of time is a very important issue with these kind of embedded communication appliances, which needs to manage a variety of tariff structures. Other RTOS features, its bootstrapping support, headless operation. They really do not have an display to show the status. In many cases, you have some kind of, if you want to flag an error, some kind of external hardware interface has to be provided, not really a display. And you have APIs. Now, when you develop an application with reference to an OS, you will be using these APIs. So, there will be multiple threads or processes. In fact, API provides you with the facility to create threads as well as processes, and they will provide support for semaphores with priority inheritance. And we have discussed and we have seen why priority inheritance is so very important when you are scheduling real-time tasks. So, typically they come with priority inheritance and the semaphore support and ability to create multiple threads with fixed priority scheduling. Also, there are features for inter-process communication. The most common thing is message queues. If there are two processes needs to communicate, how do they do it? So, you can think in terms of a message queue, a standard, a producer consumer kind of a scenario. So, a producer puts in message from one end to the message queue, and the consumer removes messages from the other end of the message queue. Okay? It's a kind of a buffer. You can consider a simplest implementation of these in terms of a buffer, and so it's a bounded buffer. So when the buffer is empty, obviously consumer is stopped from accessing it, and when the buffer is full, producer is stopped from writing onto it. But there could be various other ways also to implement message queues. In fact, it can be a complete asynchronous implementation where the messages are posted, messages are received, the process continues its own execution and may come back at an appropriate point in time to check the message queue and take appropriate action. Timers and clock management. In fact, this is a very key feature. It has to be definitely there. Device drivers, there may be a set of device drivers available, and your network protocol stack and graphic support are optional depending on what kind of service you are really trying to provide. So, if you look at RTOS kernel, see all these features have to be provided through real-time OS kernel, and we are seeing the same diagram. In fact, real-time kernels can be these pure newly written real-time kernels, or it can be a modified kernels of standard OS. Okay. So, if you look into it, this is why we are going back to the standard OS diagram. Okay. The only difference here is the kernel area would be modified with a different scheduling scheme and the scheduling strategy. Okay. And here you have a real-time kernel. So, what are the functionalities of a real-time kernel? Obviously, the processor management is a key, memory management and timer management. Among the devices, timer is the most important device and it has to be universally managed. Other devices are actually picked up depending on whether they are available or not. The other thing is task management, that is resume, wait, start, etc., and inter-task communication and synchronization for shared resources. So, what we shall see is that with reference to Linux, how does this RTOS kernel features are provided? There are various strategies which have been followed to enhance Linux kernel to provide these features. In fact, that gives you what I already said, that two basic approaches: writing a real-time kernel or modifying an existing kernel for enabling these services. So, why Linux? The basic idea is why Linux is on the upswing for use in embedded systems. It has got a rich multitasking support, security and protection. It has also got a networking support. Although I said networking may not be a key issue, but many ways networking today, many of the embedded systems are coming with networking features, multimedia support and variety of device drivers which are available on Linux, and standard and known environment and APIs. So, the familiar environment for many users and developers as well as POSIX compliance. So, all these features make Linux a popular choice. In fact, there are other features as well, other reasons as well. So, it is the cost factor, the open source factor, you have got the source code which is allowing what we say the picking inside the hood and customizing as necessary, which is not true if you are really working with a commercial OS. And popularity factor based on excellent documentation and excellent third-party documentation. Although it is not always true for each and every aspect of Linux, but the whole idea is that if there is a problem, you get variety of support. That's the basic commercial consideration for making a choice about Linux. So, the other thing, so what happens is with the Linux, if you have a modular kernel, you are possible to configure the kernel to suitable size. Okay. So, Linux is organized, embedded Linux is what we say that when Linux is organized in terms of a collection of modular components in the kernel. You have got a customizable root file system and lots of utilities. If you look at from a high-end embedded systems point of view, it is a high availability in the sense, what is availability of a software system? Availability means that if I distinguish between reliability and availability, reliability is what? The time for which it would work without a failure, that the probability is that for a certain time period the OS would work without a failure. Availability is what? Even if there is a failure, there is a ability to catch that exception and come back soon enough so that the services can be restored. So that makes a OS more available. Okay. So the probability is that when we talk about availability of a software system, we accept that there may be failures, there may be exceptions, and modulo such failures, OS has the ability to come back and restore the service. So this is how availability is distinguished from that of reliability. Also there is clustering, ability to cluster multiple systems, and symmetric multiprocessing support. Okay. So if you have a multiple processors, you can use them through this OS. These are primarily high-end applications. If you are really looking at more complex computations to be done, then only these issues become important. So you've got the Linux API, and the most important aspect of the API is a tasking. And here what happens? A process, in the Linux API, you work in terms of processes. A process encapsulates a thread of control and an address space. Address space may be shared, giving threads in effect. That means there are multiple threads within a process boundary, and processes a schedulable entity. In fact, threads in a way are processes to the Linux kernel, and they are scheduled by Linux kernel, and can be created such that they share the address space with parent process, effectively giving threads. So what we are talking about is two ways of leading to threads. So I can talk about processes being schedulable entities, and process can consist of a set of threads which share the address space. I can look at threads which are equivalent to processes for Linux kernel. So threads now become schedulable entities, and a set of threads grouped together as a process so that they share a common address space. Okay. So this can be done for your application using standard Linux API. So if you look at typically a Linux internals architecture is, here we are looking at as a key issue is process scheduler. Okay. You can have a multimedia support, you can have inter-process communication, you have networking support, and this is linked to the core mechanisms. Okay. Now what you would do, you would select the modules which are available in terms of the modular architecture, device drivers which are available, put together and construct this architecture. Okay. Because this process scheduler would manage all these processes, okay, and because they are of different nature, and that's why they are all linked to process scheduler. Depending on what kind of tasks you will have the corresponding module configured for your particular version. So what are schedulable entities? Schedulable entities, I already talked about processes, okay, or threads. Threads are also processes if you go via that path. And so you can have what is called two distinct classes, real-time class or time sharing class. When we talk about a time sharing class, obviously what we are implying is that for this task there are no deadline to be met. Application processes can have application defined priority as well as higher priority than time sharing processes. And what are non-schedulable entities? It would have interrupts or interrupt handlers, can have priorities and can be nested, but they are not schedulable. Why they are not schedulable? In the sense when such an interrupt arrives, that interrupts have to be serviced, and priorities between the interrupts means either how they are to be resolved when simultaneously more than interrupt is pending, or when a particular interrupt in service, whether you would accommodate another interrupt while that is being serviced. Okay. So that organization can be done through the OS as well, because OS has to disable the interrupts. Okay. If there are maskable interrupts, OS will disable those interrupts. So while a particular interrupt is being serviced, other interrupt will not be entertained. So that is again a configurable aspect. But there are some problems obviously which is there. One is a timer granularity. In standard Linux, the timer is set to expire at 10 millisecond intervals, because this is the smallest interval that you can really have depending on the way the OS has been configured. So the granularity can become problematic. That means you cannot have a deadline specified at a granularity lower than 10 millisecond level. Scheduler predictability, scheduler keeps tasks in an unsorted list. Okay. So requires a scan of all tasks to make a scheduling decision, so that has an overhead, and so it will scale poorly as the number of tasks increases. If you have a more real-time tasks, then obviously there will be a problem. And various subsystems are not designed for real-time use. Obviously network protocol stack, file system, Windows Manager, they are not required. You can say that they are not needed also in various embedded systems. When they are not needed, they really do not cause a problem, but when they are needed, they do cause a problem. So how do you modify, or the basic issue is that how do you deal with the Linux kernel and bring in this kind of real-time features? Currently on the, if you look at the different flavors of Linux that is available, the approaches that have been followed are the following: compliant kernel approach, dual kernel approach, core kernel approach, and resource kernel approach. So these in fact in a way are examples of how you architect an operating system. Okay? We have looked at features of an operating system. We have not really looked at how you architect an operating system. So what we are looking at with reference to Linux, how you architect such an operating system. So a compliant kernel approach is based on this basic philosophy. You have got a Linux kernel, which all of us know, and you have got these Linux development tools and environment which uses standard Linux system call API to develop an application. But you do not have a real-time feature on this Linux kernel. So what you do, you write a kernel, okay, which is a real-time kernel, but it provides the same API as that of the original Linux API. So that gives you a compliant kernel approach. Okay? So what we say, the basic philosophy wise, the Linux is defined by its API and not by its internal implementation. For an application developer, Linux is defined by its API and not by its internal implementation. Okay? So the real-time kernel is strictly a non-Linux kernel. You can provide your own kernel as such with an API same as that of the Linux kernel. So in this case, what are the implications? You really have no benefits from the Linux kernel. You're not possible to benefit from Linux kernel evolution, how the Linux kernel changes over time, because that's again one of the issues. It's an open software. It is evolving on a continuous basis. Not possible to use Linux hardware support, not possible to use Linux device drivers. Okay? So these are things which has to be developed as part of your compliant kernel approach. So compliance is, if you have a 100% Linux API, then it would support all of Linux kernel API and all of Linux kernel applications, applications which are built upon the Linux kernel system calls. So any Linux application therefore can run on real-time kernel. Development can be done on Linux host, which is set of host tools for development. This is the basic advantage. All Linux libraries are trivially available to run on real-time kernel, so all third-party software comes in. But achieving 100% Linux API is non-trivial. So consider the amount of effort put on Linux kernel development which has taken place in a generic fashion. Okay? So this what we are trying to look at as a trade-off of a compliant kernel approach. What could be the alternative? Alternative is a dual kernel approach. And here what we say, one of these dual kernel approach is a thin kernel approach. So you have got at this layer as a real-time kernel, RT Linux, okay, and your Linux kernel, classical Linux kernel, becomes a task under real-time kernel, okay. So your user processes, these Linux processes, they can be run on the Linux kernel, and your real-time tasks get scheduled by the real-time kernel. And in fact, in a way, this you can consider a set of so-called aperiodic tasks, if you go back to our original model, which does not have a real time. So that gets scheduled by the Linux kernel. So in fact, real-time kernel schedules Linux kernel, and Linux kernel in turn schedules user processes which are not necessarily real-time processes. Okay. So real-time tasks do not use the Linux API or the Linux facilities. Failure in any real-time task may crash the system because it is going through this path. Okay. So the whole development is that real-time task need not be based on Linux API. The other approach is core kernel approach, where you make the kernel more suitable for real time. Ensure that the impact of changes is localized so that kernel upgrades can be easily incorporated and kernel reliability and scalability is not compromised. So there are two ways to do it. One is a static configuration, can be configured at compile time. Other is dynamic configuration using loadable kernel modules. That is, in the runtime, you make some of the modules enabled. Now, in this case, obviously, what you assume is that you have a secondary storage where you have the OS information by which, from which you can actually add on the modules on demand. So the core kernel approach allows the use of most of it, if not all existing Linux primitives, applications and tools, and allows use of most existing device drivers written to support Linux. Okay. But if you are trying to play with the core kernel, then it can affect robustness, but in a way, since source is available, this is still a possible way to architect a Linux system for a real-time application. The other approach is that of a resource kernel. Here conceptually, it is a distinct approach from that of what we had considered so far, but philosophically it is closer to that of a dual kernel approach. So what we say, a resource kernel is a kernel that provides to applications timely, guaranteed and enforced access to system resources, allows applications to specify only their resource demands, leaving the kernel to satisfy those demands using hidden management schemes. Okay. In fact, this is architecturally a much advanced version and a flexible version compared to others. So what is the protection in resource kernels? Each application or a group of collaborating applications operates in a conceptual virtual machine. Okay. A machine which consists of a well-defined and guaranteed portion of system resources, that of CPU capacity, disk bandwidth, network bandwidth and memory resource. Okay. Multiple virtual machines can run simultaneously on the same physical machine. So guarantees available to each reserve set is valid despite the presence of other potentially misbehaving applications using other reserve sets. So what does that mean? Conceptually, I am reserving the resources, giving to a set of tasks. So effectively, for that set of tasks, with the given set of resources allocated in a static fashion becomes the definition of a virtual machine. For that set of processes, other processes really do not exist, because it has got, that set of processes has got a view of the system which consists of only those of resources allocated to it. So if you have this resource kernel, so this is the Linux kernel, these are the Linux processes. You can have Linux process running under Linux kernel, but these other Linux processes can communicate via resource kernel. So resource kernel makes what? Makes reservation of the resources for this Linux process with respect to the Linux kernel, and these resources are made available to the Linux processes. So that Linux process, this process runs with reference to a virtual machine. Is the idea clear? Each process has got a resource demand. So resource kernel handles those resource demands. So effectively it's make reservations of those resources with reference to Linux kernel. Okay. So Linux kernel knows that this much resource has been already allocated. So that gets allocated to a Linux process. So the Linux process which refers to resource kernel operates effectively in a virtual machine. So this is related to two basic concepts which we talk about reserve. Reserve is a share of a single resource. There can be temporal reserves, there can be spatial reserves. Temporal reserves are parameters which declare portion and time frame of resource usage. CPU time, link bandwidth, disk bandwidth. These are effectively a temporal resources. Spatial reserves, amount of space. it can be memory pages, network buffers. So everything gets allocated to a process via resource kernel. And resource set is a set of resource reserves. Okay. So what we do with these resource reserves? Effectively, this isolates one process from another process. So there they do not disturb each other, and these processes are guaranteed operating conditions and the timing parameters because they have got guaranteed resources. Next, what we should look at is that problem of dealing with power, okay? Because so far we have not considered power as a resource, but fundamentally in an embedded system, power is a critical resource. Now we have to see how these OSs can be adapted in order to manage power. So what kind of support we expect in operating systems for dealing with power? Operating system, it should have the ability for the application, operating system and hardware to exchange energy, power and performance related information efficiently, because then only the OS can think about power driven scheduling policies. So it should facilitate a continuous dialogue and adaptation between OS and applications. Okay. It should facilitate implementation of power aware OS services, because so far services and what we talked about for a real time, we wanted to have a deadline or an upper bound of the time with regard to services. Okay. Now we would like to have services which would provide me the power management features. So what we say that power aware OS services by providing a software interface to low power devices. In fact, in a way, what we are looking at a power aware API to the end user that enables one to implement energy efficient RTOS services and applications. Okay. So just like we were talking about Linux API in terms of an OS, using the API we create processes and threads and they become the schedulable entities meeting the deadlines. In the same way, we would like to have APIs through which we can create power aware services, and these API implementation in conjunction with the other OS services can enable me to manage power. So power aware API should provide services like processor frequency scaling and low power state transitions, and we have looked at these in the context of power aware architecture, when we said that each processor can have different states corresponding to different amount of energy consumptions, as well as we have seen that I can select dynamically the supply voltages and have the frequency scaling which dictates my energy consumption depending on the deadline. That example we had gone through. So these kind of services is what API should provide for. The other issue is ability to monitor battery status. Now battery becomes a device. Okay, so far we had not really considered battery as a device. The power supply basically becomes a device. I need an interface to that device so that I can monitor its health. And I would need also appropriate routines, or these are again system calls to control energy speed and energy accuracy knobs available on IO devices. That means if you remember, we talked about flexible applications. We discussed flexible applications with reference to timing considerations. Now we should have flexibility and ability to deal with flexible applications in relation to its energy consumption. So a power aware software architecture would something like this, that you have got an application sitting on top, you have got a power aware API, this is the power aware middleware, this is POSIX compliant OS that we are talking about with relation to the real time requirements, and this is power aware OS services that should be provided, and that is modified OS services which is an add-on, and that would work on a kind of an abstraction of the underlying hardware. Because if I am talking about a OS, now there would be variety of processors. Processors would have different power saving states. We have seen that PowerPC has got some set of states which is different from other processors. Okay, so there we need to have some kind of an abstraction so that when you are talking about a generic service, you can have an abstraction over these hardwares. So conceptually, a power aware API should interfaces applications and OS, making the power aware OS services available to application writer. PowerAware operating system layer implements a modified OS services and active components such as the dynamic power manager. And PowerAware hardware abstraction layer would interface OS and hardware, making the power control knobs available to OS programmer. Okay. What is power control knobs? Just take a simple example. If I have the ability to modify the supply voltage, okay, ability to control the frequency of operation. If it's a flexible application, do we have the ability to modify them? So an example, dynamic power management algorithm could be a predictive RMS rate monotonic schedule, but it's a low power scheduling. So just like a rate monotonic, we can assume that periodic tasks and deadline coincides with that of a period. Now it's a predictive scheduler implementation, so there would be an admission control. So I can have an admission control that whether the power budget permits that to be executed as well as meeting the deadline. And you can have a static slowdown factor, because if you have a longish deadline, I can slow down the processor. I can have a dynamic slowdown factor computation depending on how much time required to finish the execution, and that has to be combined with your deadline management. Okay. So what we say, the processor frequency and voltage is scaled according to the time predicted by the OS. Okay. The OS can provide a prediction on the basis of the computation time required by the task. The application can also predict the execution time in order to enhance accuracy. Okay. If you have this prediction, then only you can do what? Alter the processor speed to deal with the energy. Then only you would know that if I now slow down the processor, whether I can meet the deadline. Okay. In fact, we have seen that by slowing down the processor, I can have optimal energy consumption as well as ability to meet the deadline. But for all these things, we need to have a prediction of the execution time. So if I have an RPM, if I have an this RMS, rate monotonic scheduling, so I know the periodicity, along with if I know the execution time prediction correctly, then I can decide over each period what may be the frequency of operation. So that becomes a key issue of dynamic power management algorithm, a scheduler with a PowerAware application. In fact, there are also ability, you may have the ability to use application level knob, which is actually something very similar to a flexible application. So it can be an image compression algorithm. You trade off your image quality against energy available by varying the compression parameters such as bits per pixel. Okay. So the image compression algorithm is run in a continuous loop with a battery, maybe polling every 10 seconds, because you are trying to find out the battery life. A simple power trade-off policy is added to adapt the quality of the image against the battery voltage left. So here again trade-off is coming from where? If your compression is less, it will consume more memory, okay, when you are storing in the flash, but your processor is spending less time in compression. So you are trading off. So you have the, in such cases, particularly I told you in the earlier also, these multimedia applications have got this flexibility. Okay, so you can use this flexibility to deal with your deadline requirements as well as your even energy requirements. Actually, there is again a standard, just like we had a POSIX standard for real time, you have a ACPI standard, Advanced Configuration and Power Management Interface Standard. This is an open industry standard for power management services. The basic philosophy is built on the software architecture we had discussed. It provides basic power management and abstraction of the hardware. Okay. So basically, what are the features? It would provide ways for the system to describe its device configuration and power control hardware interface to the operating system. Okay. Because OS needs to know this information, so provides a standard way. It also provides mechanisms for thermal management and also on mechanisms to specify devices, resources and its control mechanisms. In fact, when we are talking about the hardware abstraction, ACPI supports a kind of a general power states, okay? A set of power states which are abstraction over the power states that the processor may support. So the power states are G3, one is mechanical off, system consumes no power. G2 is a soft off state which requires full OS reboot to restore the machine to working conditions. It can have several substates, S1, S2, S3, S4, and these substates are depending on how much information is actually retained. Say for example, for S2, it's a low wake up latency state without loss of CPU and system cache state. Okay? So that means if the system has to reboot or reinitialize, it knows what kind of system context information is available. So that's how the states have been classified. So it's not a processor dependent, but it's a kind of a processor independent characterization of the power states. Then you have got G1, a sleeping state appears to be off and the time required to return to working condition is inversely proportional to the power consumption. Okay? But in this case, what is interesting? I am not talking about rebooting of the system. And G0 is a working, fully functional state, and there is a legacy state which may not be strictly ACPI compliant. So there should be a power transition diagram. So if you had a mechanically off, from mechanical you go to a legacy state, and there you can go to a G0, which is a working state which is ACPI compliant. That means you can make ACPI calls, compliant calls in this state. You can go to sleeping mode, you can go to soft off mode, which is your G2, okay? And there are a variety of these different modes in which you can go, and your BIOS routine, basic IO routines would come into play corresponding to the different modes in which the system is. So what are the functional areas? Functional areas, it addresses a system, obviously power management, device power management, because devices have got their own power consumptions which is different from that of your processor, and describe devices, the power states, power planes the devices are connected to, and controls for putting devices into different power states. Okay? So it's a low level control knobs depending on the devices. So you have got processor performance management. So you have the DPM, dynamic power management software, to decide upon the scheduling scheme. And well, the OS is idle but not sleeping, it will use commands described by the ACPI to put processors in low power states if that is the need be. Then plug and play, which is compliant with the standard applications, and that it offers another interesting thing is a general event mechanism for system events such as thermal events. Okay? Power management events like docking, device insertions and removal. So these thermal events, thermal implications, if the temperature goes beyond a temperature limit, okay, on the processor when it's working and working vigorously, if the temperature goes beyond the limit, what kind of action to be done? A thermal shutdown. So this is a thermal event. Who shuts down it? The OS should shut down it, and ACPI provides the compliant call and an interface to detect such an event. It also provides this battery management subsystem. That means it provides the standards for that interfacing. Okay? And thermal management provides a model to allow OEMs to define thermal zones, thermal indicators and methods for cooling thermal zones. Okay? So this has to be controlled by some other device, and those devices can be related to the OS itself. Say for example, I would like to put in a control signal to increase speed of the fan to cool. Okay? So those kind of interfaces should be provided for the OS to manage the devices. So these are basic ACPI functionalities, and the lowest level functionality allows, this is the standard hardware software interface between OS and embedded controller, allows any operating system to provide a standard bus space interface, allowing the drivers to communicate with and use the resources of the system of embedded controllers. Okay? Standard bus based controller, so you have the basic interface provided through ACPI through these devices for doing this kind of energy oriented management. Okay? So that's a low level hardware software interface, because there will be hardware signals required also to provide this kind of functionalities and the service. The other thing which we have not touched upon related to the OS is basically the middleware when they are really connected via the network system. you have the issues related to the real-time database and real-time remote objects, that is functionalities or the services in a client-server mechanism. The basic issue in both these cases is when it's a real-time database, there has to be a consistency, because when an update of the database has to take place, that update has to take place with the timing deadlines. So, these update, if it has to be implemented, in many cases that databases are managed in the memory itself and not with respect to the disk. Okay. When you are talking about access to remote objects, what do you try to provide? You try to provide the end-to-end communication with a timing deadline. And in fact, these real-time database and others are becoming very important in the context of today's, if you are gathering information from an external environment and trying to store the data, a sensor network kind of an application. In such a scenario, you need to maintain these databases, okay, and those updates have to be in real time and should satisfy the deadlines. So, this takes us to the end of the features that we had referred to for OS in an embedded system. We have examined basic features of the OS, which is targeted for this kind of applications, how to architect such a system. We have also examined mechanisms suggested for power management. So, if you have any questions, we can refer to them. See, the basic question is that time resolution. So, see, you have the timers. Timers can be set to generate interrupts at fixed intervals. Now, these intervals are real time, okay, and the real time has to be internally represented by the OS. Now, if OS allocates a fixed word size to represent the time, then the resolution is fixed, okay. So, the granularity of the time depends on how the OS manages that time data structure. It also is related to the underlying hardware, because if your timer cannot support a variety of resolutions or a very fine resolution depending on the clock at which it is operating, obviously even if OS supports lower granularity of time, it has got no meaning. Okay.